And welcome everybody. We have made it to chapter 9. So we are continuing our discussion on these more complex circuits where we've got series parallel combinations. And instead of relying strictly on algebra this time, we're going to try a different approach. And we're going to look at, first, we're going to look at a network theorem called Thevenin's, where Thevenin's and Norton's both, they're kind of interchangeable, and you'll see why eventually. But their main function is to allow us to use different values for load resistors and change them out in a very simplified circuit. If we have a very complex network of resistors, series and parallel, and we want to know how, let's say, 5 different loads operate in this circuit that we've built, it's a lot easier to condense it down to its essential functionality, which we're going to use as a single voltage source and a resistor in series. We're going to reduce the whole thing down to that, and then we can easily change out however many loads that we want in a 2-resistor series circuit. So that's the goal here. We're trying to simplify the process of which load should we use if we were design engineers trying to decide how our circuitry performed for whatever we were trying to drive. Okay? So I've come up with a list of steps that we're going to use to take. It's a little bit different approach, like I said, than mesh and nodal. Those rely more on your algebra skills and KVL and KCL. And this is going to look at everything from the perspective of the load resistor. We're going to find our resistance at the load resistor. We're going to find the voltage at the terminals where that load resistor is located. Okay, so here we go. So Thevenin's, the very first thing that we're going to do is we take our circuit and we're going to find what's called the Thevenin resistance, and that's R sub TH, Thevenin resistance. This is not the total resistance, even though letter A refers to total. I'm going to show you why that's referring, after we decide that we're going to find the RTH, we have to come in here and find the RT between the terminals. So we remove the load resistor, and we typically label those A and B, where the two legs of the resistor connect to the circuit. And then we act as if an ohm meter is placed in between those terminals. Okay, now, to make sure that we do this correctly, you can't leave the voltage source in and you can't leave any current sources in. You have to short the voltage sources and open all current sources. Then you can find the total resistance, and you work just like Chapter 7 with the series parallel reduction techniques. Once you have RH calculated, the next thing you're going to do is find VTH. So we go back to the original schematic, remove the load resistor again. So in both cases here, we're taking the load resistor out. And a lot of times you'll see me not even give the load resistor a value in the original schematic. I'll just call it R sub L, because it doesn't matter what the load resistor value is when we do this method. So remove the load resistor, and now we're going to find the open circuit voltage, or the voltage of A sub B. You know, while that circuit is running, if we were to put a voltmeter across A and B, that would give us the open circuit voltage at that point where the load resistor is going to be located. Okay. Once we find that, we have enough to draw our Thevenin equivalent circuit, which is a Thevenin equivalent voltage in series with a Thevenin equivalent resistance. Once we find those two things, we can put as many load resistors as we want here and switch them out and look, 4 or 5 different loads, whatever. But we now have a 2-resistor series circuit that we can easily analyze, as opposed to doing 5 circuits where we have to do the entire, go all the way back to Chapter 7 and do all of those steps for every single load that we want to look at. This allows us to do that very, very quickly. We have to do one analysis, right, where we have to get it down to this point. But once it's in this format, it's very, very easy to see how different loads perform. Okay, so that's the goal that we're going to try to accomplish here. And we're going to look at some different types of series parallel circuits. I'm going to start out with a fairly simple one, and then we'll start ratcheting up the pressure. So here's the very first circuit that we're going to take a look at. And if we were just doing Chapter 7 techniques, then this one wouldn't be too awful bad. We've got just 2 blocks here. We've got a couple of things that are in parallel with this one resistor, but that's it. Okay, so not too awful bad. So the first thing I'm going to do is I'm going to find RTH. Now, if you want to find VTH first, that's fine. It doesn't matter which order you do this in. I always find RTH first. Okay? So we remove the load resistor, we short out voltage sources, and we open current sources. So this is what it looks like. I'm going to move this over a bit. I'm going to show over here on the left that this voltage source has been shorted out. There's 200. There's 400. Whoops, sorry. This one is 600. This one is 400. 1K. And there's my open terminals, A and B. So it's as if we place an ohm meter here between those two terminals. Okay? All right. So it looks a little different because we're coming from, this time we're going to start farthest away from the meter, which would be over here on the left, and work ourselves right. Normally in this format, we work ourselves back to the source. In this case, we're going to work the opposite way just because that's where the load resistor is. Okay? So I'm not going to do anything different. If you need to, you can flip this 180 degrees just so the meter's on the left-hand side, and then you will be working right to left. But you're still working farthest away back to the meter. So I've got, instead of covering up this side, I'm going to cover up this side and say all I care about is the farthest two branches that are in parallel with each other, which is this one and this one. Remember, I look at this as just a piece of wire. This is shorted out. I don't know that there is a source there. Okay, I'm just looking at this problem. So it looks like that in parallel here, my REQ is 600. Well, I didn't mean to do that. 600 in parallel with 600. That makes it easy though, because the answer to that is 300. So that makes this. And now I'm at an essentially series circuit. And so my RTH is 1K plus 300. So that's 1.3 kiloohms. So RTH, 1.3 kilo. Right? Now, I can erase this, and I'm going to forget about it because I don't want it to influence what I'm doing in this next part. You have to do these calculations in a silo. Okay? So the next thing I'm going to do is find my VTH. Okay, now, again, I remove the load, but I leave the source in, and I do it as a regular problem. Okay? So, rewrite this here. I can, let's rewrite it. 15 volts, 200. I just want to forget about that 400, don't I? 600 ohms. 1K, A, and B. Now this time it's as if we place a voltmeter between those two terminals. Okay. So your first question may be, just like my first question was, what do we do about this? Okay. If this wasn't here, if we just had a load resistor that was in parallel with this 600, then you could easily see that we'd just be looking at the voltage across the 600 in this 3 resistor series circuit, right? We're just putting our ohm meter there. But what happens when you got one of these? What if you got one down here too? That's the circuit we're still working on. I'm just shooting here for a second. So if you have either of these, they're what we call a hanging resistor. These are not they are simply conductors. So you look at a short or a piece of wire, that's it. They have no influence on you making this measurement right here, because remember, essentially what you're doing, since we've talked about chapter 7 and we know about meter loading, what are you doing over here? You're really putting in a resistor. And let's say it's a 10 mega ohm resistor. Who cares about this extra 1500? It doesn't matter what those values are. You're making this total resistance on this branch over here higher and higher and higher. So it'll have less and less effect the more resistance you pile. It'll less and less as the much higher over here. So that's what you're doing. If you have, it's still 5 mega ohm instead of 10 mega ohm. So those are hanging resistors. They are not included in the calculation, even though it looks like it should be, right? Because, you know, well, there was a resistor there, so we should probably do something with it. No, that is not the case. So we are just going to look at the 600 ohm, and now I just have a voltage division problem. I've got 15 volts times 600 over, what's the total resistance here? That's 200 plus 600 plus 400. Again, this does not count in any calculation here. That's a hanging resistor. I ignore it. 200 plus 600 plus 400 gives me 1200. So that's going to be 7.5 volts. So VTH equals 7.5 volts. Okay. So now that I have those two things, I can go ahead and write my Thevenin equivalent circuit. So we said 1.3 kilo ohms, and we also said 7.5 volts. There it is. That's my Thevenin equivalent circuit. Now I'm going to load it. Oh, let's say it's a 500 ohm. Let's say this is equal to 500 ohms. See, we haven't even needed this value until right now, until we finally do our final analysis here. So now I just have a 2 resistor series circuit. So I typically want to know what's the voltage of the load and what's the current through the load. So the voltage on the load, getting ahead of myself. Just voltage division, 7.5 volts times 500 over 1.8K, which is 1.3 plus 500. I haven't had to use my calculator yet. So that's 2.08 volts. And let's look at the current. So the current is going to be the voltage of 2.08 volts divided by the resistance of 500 ohms. So I just take that value divided by 500, and I get 4.17 milliamps. So as usual, let's consult Google, not Google, but Multisim, and see how we did. Okay, I've built both circuits in Multisim, and if I've done this correctly, then they both should give me the same exact answer. So I'm going to go ahead and grab a multimeter. I'm going to put it around this 500 ohm, and I'm going to grab another multimeter and put it around this 500 ohm. There's this. There's this, and I'm also going to measure the current on each circuit. I'm going to have to reverse this probe. Okay, so here we go. All right, so we expected 4.17 milliamps and a 2.08 volt drop, and looks like that's exactly what we found. All right, very good. On to the next one. And here we go. Here is the next example. And so we've added an extra branch over there, and got a little bit higher value for the source. So let's see how this will play out. Okay, so the first thing I'm going to do is find my RTH. And I'm going to short my voltage source. I'm going to pull out my resistor. So this one is not going to be a simple calculation this time. And get get this RTH out of the way, put it over here. Showing that the source has been shorted. So I've got 100, 150, 200. I just went by 50s for some of this. 250, 300, 350, 400, 500. Okay, and there's A, and there's B, and there's my ohm meter. Okay. So again, I'm going to start furthest away from the meter, and I just want to consider this branch and this branch. That's all I'm looking at. So one of these branches has 150 in series with 100 in series with 200, which gives me 450. So this is going to be REQ equals 450 in parallel with 250 plus 300 on this branch gives me 550. So let's see what that is. So 1 divided by 450 plus 1 divided by 550, take the whole thing to the negative 1, I get 248 ohms. Okay, now we're not done like the other one. Now we have to rewrite this and put that resistor in between the green terminals. So this is 350, this is 248, this is 400, and 500. So we got to do one more parallel combination here, and that is between this branch. If we go orange this time, so now I'm only considering this branch and this branch, and so I've got what, 350 plus 248, which is 598. So now my REQ is, what did I say, 598? And then that's in parallel with the 400. So let's calculate that. 1 divided by 598 plus 1 divided by 400. Take the whole thing to the negative 1. 240. And so now if we replace that, we're down to an essentially series circuit. I know I'm running out of room over here, but so that is 240 and then 500. So my total, or my RTH, is going to be 740 ohms. Okay? So again, I had to do a couple more series parallel reductions. That's okay. We are experts at those now. All right, now it's time to find VTH. And, excuse me, I'm going to open this up over here. Okay, so I've got 50 volts. 50, 200, 250, 300. 350, 400. Okay, now remember, this is a hanging resistor. I'll draw it in here. But it is not included in our calculation. Okay, so really I'm looking to analyze this circuit with just looking at this 400. I want to know what the voltage is across that 400 ohm resistor. Okay. So now I have a choice. Excuse me. I can use Chapter 7 techniques. I can use mesh. I can use nodal. And I think what I'm going to do is I'm just going to use Chapter 7 because I don't want to write a bunch of equations if I only have these two boxes here. Because I think it'll be quicker in this instance to do it with Chapter 7. So I'm just going to find the total resistance here. So if we're only considering from here to here, I just need to do one parallel combination. And again, I ignore all of that. It's the 350 and the 400 that are in series together. So the RT, it's going to be, these are all in series. right? And so that's going to be at the front here. So 100 plus 150 plus 200. Those are all in series with the source, okay? So really I'm just looking for this parallel combination. So plus 550 in parallel with 750. So let's see what that is. So this is going to give me 450 plus this 1 divided by 550 plus 1 divided by 750. Take the whole thing to the -1, and I get, oh, that's 50/50. That's not right. This is 550. And now I get 317 ohms. Okay, so my resistance total is going to be 767. Okay, now remember, this is my total because I'm doing this in a silo here. I don't care about what this was because that's a different thing that I did. I'm trying to find this voltage with this circuit. So now my total resistance is 767. So that's my R total in the second part here. So now I'm going to rewrite this circuit. And those were 317 in parallel. So what I'm going to do is I've got a current coming in here. And so the current total is going to be 50 volts divided by the total here of 767. And then that's 65.2 milliamps. Okay? So that's what I have coming into this node. 65.2. And that's going to split part of it here and then part of it here. Okay? So again, those two in parallel were 317. So I need to know that number. So if I want to find, I'm just going to find the current through this branch because I don't really care about this one. This is the one I'm after. And I'm just going to assume that I'm doing this correctly. So the current through the 350 and the 400 is 65.2 milliamps times the total is 317. The individual branch is 750. Do that calculation, and I get 27.6. Does that make sense? That makes sense. Milliamps. Okay. So now, if I know that, I can say the voltage of the 400 is equal to 27.6 milliamps times 400 ohms, and that'll give me the voltage drop. And that's 11.0 volts, just like that. Okay, so that means now that my VTH is equal to 11.0 volts. Okay, now I have enough for my Thevenin equivalent circuit. Thank goodness we only had to do that once, and that we didn't have to do series parallel for 3 or 4 different loads. I know I'm only doing one load here. But okay, so my Thevenin equivalent circuit, I've got 740 ohms and I've got 11 volts. Okay. And, what should we make this? Let's make it an RL equals 200 ohms. So here we go. There's my circuit. And so now if I want to find the voltage on the load, that's going to be 11 times 200 over, add those together, and you get 940. .34. And so then the current is going to be 2.34 volts divided by 200 ohms. And I get 11.7 milliamps. Okay, well, let's consult Multisim and see how we did. And so again, if I've got this correct, then Multisim will tell me I've got the exact same circuit, the original schematic here, and then I have our Thevenin equivalent here. So I'm going to go ahead and put a voltmeter around our load resistor and see if we get the same voltage in both cases. And then I will put an ammeter in each one. I want to know that branch, reverse it. And I want to know that branch. Okay, let's see how we did. So we expected 11.7 milliamps of current, and we expected 2.34 volts across the load, and it looks like that's exactly what we got. Let's go ahead and show the voltage. 2.34, as we expected. All right, very good. One more example. Okay, so now we're going to revisit our good friend, the Wheatstone bridge, and this time we're going to do it with Thevenins. Okay. Now, this is a little bit different than the other types of circuits, and I'll show you why. Okay, when I go to do the RTH, okay, since I can't ask you this question in class, because this is one of my favorite questions to ask, there's the shorted out source. And we have the load removed here. And so here's my 6K and my 10K and my 4K and my 5K. So the question I ask is, and if you want to pause it after I ask the question and see if you can come up with it, see if you got the right answer. How do you find RTH if you put an ohm meter between here? What is in series with what? What is in parallel with what? To me, it's not intuitive because, you know, you might think, well, these two are in series, so you add them together. And these two are in series, so you add them together. You have to remember, the probes are now at two just random points in the circuit here. So that's what everything is referenced on, okay? So you can't just add everything up and then take them in parallel. Like you can't just take this branch, 16 in parallel with 9 and get the answer, okay? So this is how we have to do it. And I'm going to show you the derivation on this. I'm going to write down my values over here. So 25, 6K, 10K, 4K, 5K. I'm going to erase all of this, and I'm going to show you where this came from, because when I first learned Thevenin, I had no idea where the equation was. There is an equation for this eventually, but I want to show you where it comes from first. Okay? So here's the generic format. We have the source that's shorted. We've got a resistor, resistor, and we've got a resistor, and we've got a resistor. And here's point A, and here's point B. Okay? It doesn't matter what those resistor values are. I'm just going to call them R1, R2, R3, R4. Okay? The label that I'm using, R2, R1, is not important. It's the position that you find your resistor in is what matters, okay? So when I give you the formula, it's going to reference what you see here, but you have to remember what each resistor represents a certain place in the schematic, okay? Now, the reason I couldn't figure this out is because I didn't know what to do with this short over here. What do you do with that, okay? So here's how I do it. I look at this as three separate branches. There's branch A, there's branch B, and there's branch C, okay? From our discussion in chapter 6, I know that it doesn't matter if I rearrange these and put C first, and A second, and B third. Whatever current was coming into this node is going to remain the same, and whatever current that leaves this node is going to remain the same, right? It might, because C is over here now, that current that was going this way just comes over here. It doesn't matter how you have the branches oriented. You can rearrange any parallel branches that you want, okay? There's no relationship as to why you have to write it A, B, C, or C, B, A, or whatever, okay? So with that in mind, I'm going to rearrange this to put the short in the middle, okay? So Now I'm not going to show the voltage short again because I've got a short in the middle. Okay, so there's still R1, R2, R3, and R4. And here's A and B. Remember, we're taking our ohmmeter and putting it between those two terminals. Okay? Would you agree, and I know you can't give me feedback in a video like this, but would you agree that a short could be that long, or that long, or that long, or that long, or it just could be a point where two things touch? Okay? I'm going to take this short and I'm going to reduce it down to a single point and redraw it. So now I've got something silly looks like this. Right? There's R3, R4, there's B, there's A, here's R1, R2. So now what I'm going to do is I'm going to take that point and stretch it out this way and then rewrite all of my resistors. So now over here you can see if I stretch this out in the middle, something like that, I have A. If I redraw this, R2, and you should start to see it makes sense. Okay? I think you can clearly see that you have these two are in parallel, and you add that to these two in parallel, and that'll give you the ohms between A and B. So the generic formula, if you label them R1, R2, R3, R4, the Thevenin equivalent here is R1 in parallel with R2. Take that and add it to R3 in parallel with R4 every time. Okay, I won't have to go over this again. I can just go straight to this. So the Wheatstone bridge is pretty quick to analyze because it's going to be this same equation every time. You have to do two parallel calculations and then you add them together. Okay, so let's go ahead and do that. And I'm going to rewrite my original circuit up here. When I first learned this back in '99 or whatever it was, I got the equation and I went home and I didn't know enough yet to figure out how that worked. And it took me a year or two, and I thought, you know, if I teach this one day, I'm going to show students where that comes from because, man, that just stuck in my craw for a couple years, and I didn't want to ask for help because I thought I could figure it out, and so every once in a while I would revisit it. And so anyway, I thought that was the best way to show you how that works. So here's 25 volts. Okay. There's B, and here is my 6K, 10K, 4K, 5K. All right, so RTH is going to be 6K in parallel with 10K plus 4K in parallel with 5K. So let's do those calculations. One divided by 6 plus 1 divided by 10, take the whole thing to the -1, I get 3.75, okay, plus 1 divided by 4 plus 1 divided by 5 to the -1 gives me 2.22. Okay, so that gives me a total of 5.97K ohms. So there's my RTH. That was easy enough. I always liked doing these because they were quicker. So that's not very readable at all, John. 5.97. I have to write around the holes. There we go. So we got half of it done. Now we got to find VTH, which now we're going to go back to the very, very first discussion in Chapter 7 on the Wheatstone bridge. And that is, I need to know what the node voltage is here and the node voltage is here, because if I'm putting a voltmeter between A and B, okay, that's the voltage of AB, or it's the open circuit voltage, just like we saw in the presentation steps, okay, of what Thevenin's theorem is. Okay, so as you know, if you have the voltage from A to B, it's the same thing as the node voltage at A minus the node voltage at B, because both of these are connected to ground here. So it's really this voltage drop subtracted from this voltage drop, or vice versa. You always want the absolute value. So if you get a negative number for this value, just put a positive on it. All you're looking for is the absolute value of the difference between node A and B. So we just have two voltage divisions here. We have VA equals 25 times, now this time it's 10K over 16K, and VB is going to be 25 times 5K over 9K. Just two simple voltage dividers. 25 times 10 divided by 16. We'll call it 15.6. And VB, 25 times 5 divided by 9, 13.9. So VAB, if I take the difference of the two, 15.6 minus 13.9 gives me 1.7 volts. So that is my VTH. So this is 1.7 volts. This is K. All right, now I'm ready for my Thevenin equivalent circuit. And again, I haven't even named what the resistor load value is going to be. This is 5.97K, and we said that this is 1.7 volts. So this may be down in the micro amps. Oh, let's call it 750 ohms. Okay. So the voltage of the load is going to be 1.7 volts times 750 over, I'm going to add those together. I don't want to have to do the math in my head. It's too late at night here. 6.72. Okay. So 1.7 times 0.75 divided by 6.72, and I get 190. 190 milli? 190 micro. Okay, because you see here, I'm sorry, millivolts, not micro. What am I doing? Millivolts. This one is by far much bigger in size than this one, and so this one is going to get the majority of the voltage. All right, so we know that from chapter 4. Okay, so this one only gets 190 millivolts. So then the current through the load is 190 millivolts divided by the 750 ohms. And we do indeed have microamps. It's 253 micro. So there's our performance characteristics of a 750 ohm resistor in this Wheatstone bridge. All right, so let's check multisim one more time and see how we did. Okay, so now we're going to look at this Wheatstone bridge in multisim, and I am going to show you one thing real quick that I haven't shown in the previous two examples, but you can measure VTH and you can measure VTH. It's super easy if you have a DMM. So let me go ahead and grab one real quick. And you can do this for the other problems that we did as well. I just wanted to get the final numbers, okay? So if you get the final numbers, you know you got it right. But if you wanted to know if you got your VTH and RTH right, here's how you would do it. So I'm just going to find VTH first because I'm already set up for it right here. All I've done is I've removed the load. There's my load over here. And I've put a DMM in its place, and it's on voltmeters. So this is the second part of the circuit that we just did. Let's see how we did. Okay, there we go. Now they're saying 1.74 volts. That's 40 millivolts higher than what we got. But I think we're okay. All right, so that is our VTH. If I want to know what the RTH is, I move this over to ohms, and I come back over here. I'm going to control X so I can control V it. I'm going to control X the source, and then I'm going to short this out. I guess I have to put a junction here, don't I? Just put one right there so that I have something to draw to over here. Okay, I don't even think you need a... let's see what it does here. There we go, 5.97 kilo ohms. So I just measured the VTH and the RTH using multisim. So super, super handy. So now I'm going to delete this. And I'm going to Control V, my source back in. And now we're going to look at the final characteristics of this resistor. Okay, so I'm going to put this resistor in here. Get rid of that. Put this in. I'm going to give myself enough room for the DMM and for the ammeter here. Okay, so now I want a DMM for each one. I'm going to measure the voltage here and measure the voltage here. This one will be the same. I guess I could have left all that stuff up, and then I'm going to put an ammeter here as well. I'm going to reverse that probe. Okay. So there's my bottom two measurements. Now for the top here, I'm going to take my multimeter and I'm going to go around that resistor, and then I'm going to put a probe in here on that branch. Reverse the probe direction. Let's see. Is it going that way? My A was what? Oh, I don't have the voltages now. I believe A was bigger than B. If not, I can. The only thing that matters here is that the A will look like it's negative. The load current should never be negative, and the load voltage should never be negative. If they are, just null out the negative sign. Okay, make sure this one's in volts, and let's hit it. So here we've got, this is saying about 194 millivolts. This one is saying 189 millivolts, so that's like 190. So we're like 4 millivolts off. I'm cool with that. And we're also about 5 microamps off, and I'm good with that as well. Okay. So some of this has been, you can see here, if I use what they used, if I change this to that 1.74 that they got, my guess is that these will be identical. There you go. Okay, that matches up much more closely. So, you know, in my rounding somewhere, I just had the 1.7 volts. Not a big deal. If you were this close in your answers, I would count it right as well. Okay? All right, so that concludes this discussion on Thevenins. And next we're going to talk about Nortons. And they're very much intertwined, and I will explain all that in the next video. Thanks for watching.